Hello, welcome to the presentation of my research project, which is Leakage-Aware Multiclass Early Detection of Docker Container Escape Behavior using Behavioral Trace Modeling. Throughout this presentation, I will demonstrate the contributions I have done and results I have obtained, and I will also demonstrate the system architecture and its reliable pipeline infrastructure. And I also will show the runtime behavior using sequence diagrams. So let's begin. I want to start with the problem definition as the introduction. As we all know, Kubernetes and Docker-based systems and also cloud systems are becoming more and more prevalent nowadays because of its lightweight and less lightweight operations and less dependency to the host operating systems when we compare it with virtual machines. More formally, it can be defined as containers are widely used in cloud, edge, and DevOps systems because they provide lightweight and portable execution. However, this may lead to some problems. We can list them as follows. Containers still share the host kernel, like the virtual machines, and if the isolation boundary is broken, the attacker may reach the host level resources. And one last vulnerability is a successful escape can enable privilege abuse, sensitive file access, or lateral movement. And the goal of this research project is how we can detect the container escape attacks in runtime security systems. This is the solution we have provided using ML and DL algorithms and its related architectures. The challenge of this research project is mainly comes from the high accuracy problems, and it can be misleading at some points because the benchmark contains structural risks. These can be listed as follows: duplicate execution records, repeated privilege patterns, limited source diversity, and strong class semblance, and lastly, shortcut prompt text contextual queues, which are very risky factors when training machine learning algorithms. They are tend to give overfitting or misleading results when these are not covered properly. But throughout this research project, each one provided with a solution, and the results are interpreted by solving these problems. And the contributions we have done by answering research questions. The main research question is how can Docker container escape behavior be represented and evaluated so that predictions reflect runtime evidence rather than dataset shortcuts? The main contributions of these problems can be listed as follows. Leakage-Aware multiclass benchmark solved as building a controlled multiclass benchmark that reduces the duplicate-driven, source-driven, and shortcut-driven overestimations. Family-level attack discrimination solved by moving beyond binary safe versus unsafe detection by separating distinct container escape behaviors. Another multi-view runtime evidence design proposed contribution is representing each execution through system call traces, return outcomes, scalar descriptions, and summarize privilege context. Behavior-centered modeling strategy solved by creating ordered system call behavior as the main predictive signal. because of the reason that it best reflects runtime attack activity. Cautions use of privileged context as auxiliary evidence. By contribution done is using capability and privilege information as auxiliary evidence to avoid learning stable context patterns as shortcuts. And the dataset and label design, which is proposed in the previous slide, and the diagram shows how we done that. We actually construct two different different solutions for that. For one of them is the coarse attack family labels, which includes safe, runtime, socket, and file system escape attacks. Includes 4 different classes, and majority of the classes in terms of numbers is considered as safe than the runtime, whereas the fine-grained attack family labels constructed by further dividing runtime execution attack class into 2 different ones, and also incorporating file system escape attack as a 2 different class, which is further enriches the dataset far from its previous implementation, which is safe versus unsafe binary, to 6 class the dataset representation, which comes far from only saying it is unsafe or safe to say what type of attack is it, which is done by pre-processing proposed in this research process. And 6 attack family benchmark. Clinch benchmark contains 48,142 containers execution records. And the task is formulated as 6-class attack family discrimination instead of binary safe versus unsafe screening. We also mentioned that. And the benign class dominates the dataset, which is a large number. In this case, 29,438 samples. While malicious classes are smaller and unevenly distributed. As we can see, they are much smaller when compared with safe, which is also another problem for training machine learning algorithms, but we solved it with our contribution that we will mention in the later slides. So let's continue. This is the pipeline and system architectures we have incorporated, which comes from all the way to the container at the Docker container escape dataset to pre-processing and artifact construction, which includes auditing, duplicate, and leakage, to parsing sequence and capabilities features, scalar feature engineering, and prefix and split metadata builders, then some lookup and tables, corrected exports, process scalar artifacts. Then all of these then feed into the machine learning algorithms, which comes from some pre-processes like tensor preparation, then feeding these into different machine learning algorithms like contextual baselines, behavior center sequence model, and visual ensembles, then training and observing the results. And in other words, raw records are standardized, audited, parsed, labeled, and converted into fixed benchmarks artifacts before model fitting. And the pipeline creates behavior, contextual, scalar split, and prefix metadata. The multi-view runtime evidence. The benchmark represents each execution record using 4 evidence views. such as ordered system call sequences, align return outcome, contextual privilege summaries, scalar trace descriptions. And along this, system call behavior is treated as a primary predictive signal. We incorporate this intuition by the experimental processes. And some data analysis phase shows that some return value entropy values and system call entropies. For example, safe class shows high entropy with high tails, whereas reverse shell tends to have less entropy in the return value. In the system call, they are mostly showing high entropies, whereas values such as sensitive file override and host file system modes tend to have smaller range in terms of entropy. Some sequence length also this showed in this page. For example, reverse shell tend to have high sequence lengths in the return value, and sensitive file override also have the same behavior, whereas process injections shows very limited sequence lengths across attack families. Same kind of figures can be seen both in the return and system call lengths. Attack families differ in trace length and entropy, which shows variation in both temporal structure and behavior diversity. Capability additions and removals describe privilege context, but stable capability patterns may become shortcuts. Prefix-based early detection, which is the some of the contributions we also done. The model is evaluated before complete trace is available to observe the differences when the prefix level differed. The runtime events are truncated at selected observation levels. Then encoded in the feature encoder level, which also have some processes. Then the output is a class probability, which provide behavior contextual inputs to the multiclass prediction transformer. Then it comes to the decision logic classifiers by feeding it as probabilities. Then there is a sum loop, compute top class confidence scores, which is the result observation. Then we are feeding it to the security dashboard to the observer of this process to select continue or raise the early warning alert, detecting the safe or unsafe condition to warning or continuing monitoring. And these are the results of this research project. These are just some of them, not all of them. The actual evaluation of results contains much more models, but for example, the attention bias TM and CNL bias TM showed in this figure with their prevalent macro F1 and loss progression graphics, as we can see from their behavior. Also, Bairguru gated recurrent unit as a sequential models also used throughout this research process. The strongest behavior-centered sequence models achieve approximately 9980 macro F1, which is really high, up to 99.90% balanced accuracy. Because of the training procedure success and also successful pre-processing. These results shows that order system behavior provides strongest predictive backbone, which also shows in the table also. And the probability prefix level reliabilities demonstrated with rock curves. Rock curves are near saturated for strong sequence models. As we can see, the statistical by LSTM almost 99.99%. But precision recall curves reveal finer differences under class imbalances, which present more separatable behaviors. We can observe their behaviors in terms of how they act from the figure, and also we demonstrated prefix level results, which shows that very early traces are difficult, and while later prefixes become more informative. For example, when we compare 75% prefix level with 100% for three-branch fusion, um, the observed trace, a macro F1 score for 75% prefix level is 87.33%, whereas when we feed into maximum level prefix percentage, which is 100, the results goes all the way to the 99.84%, which shows how informative to give full prefix levels to the models we have built. Some limitations, discussion, and feature work we can mention is as follows. The main interpretation we can get from our research is system call traces are strongest signal. They capture actual runtime behavior of container escape attempts. Privileged context is useful but not enough alone. Capability information helps explain the environment, but it can also create shortcut patterns. Leakage-Aware validation makes result more vulnerable. The benchmark controls duplicate, repeated, and shortcut prone patterns before model evaluation. And also our project some limitations and some need for feature work also. The broader dataset diversity is needed. For example, including more container images, workloads, and attack implementation can be implemented. Cross-environment validation should be strengthened. Results should be tested across different systems, configuration, and deployment settings. Early warning systems should be developed. In other words, we should deploy the model to see actual success of the system. Prefix-based detection should be extended from offline evaluation to live runtime monitoring to see real results. In conclusion, reliable Docker escape container depends on behavior-centered runtime evidence, leakage-aware benchmark construction, and prefix-aware evaluation. Multiclass attack family prediction give a more informative view than binary anomaly detection in various ways we have discussed in this presentation. Early detection becomes more reliable as runtime evidence accumulates. Thank you for listening. This is the end of the presentation.